Right, pure bending. So now we are going to, so it's a different topic now. This topic is easier, okay? Easier, less complicated. And again, I've solved this problem so much that I make up my own rules. Like the 4 rules you see on shear stress, okay? I also have my own rules that you don't get from any textbook, okay? And these rules are acquired from experience or mathematically. So if we have a structure like this, okay, so the structure is simply supported and then we have a load P over here, right? So I'm going to call this point A, and I'm going to call this point B, where the load P is, and I'm going to call this point C, and all of them, the distance from here to here is L over 2, and the distance from here to here is also L over 2. All right. So for this case, if I draw a transformation, so this is our X, Y, rotation above Z, right? So we know at point A, Y movement is equal to 0, X movement is also equal to 0. So on a free body diagram, you have 2 reactions. Okay. Whereas at point C, Y is equal to 0, but X is not equal to 0. So you only have one reaction force at CY. Okay. So anything that you allow to move, the forces is equal to 0. Anything that you restrict moment or movement, the forces is not equal to 0. Okay, that's what you see over here. So from here to calculate bending, okay, bending stress is we are calculating stresses in the x direction. Okay, normal stress in the x direction is equal to, the formula is equal to minus mz over izz multiplied by y. Okay. So this is the formula we use for pure bending, where stresses in the x direction is equal to mz over izz multiplied by y. So if you look at shearing, right? Remember we just came back from shear. When it's shear in the xy direction, for example, this will be equal to what? Vy over what? Izz, right? Qz, right? T divided by T, right? So what I'm trying to highlight is this, okay? For pure bending, is the opposite. If the moment is about the z-axis, the second moment of area is in the what? In the z-axis. Different from what? From shearing. Shearing, your shear force is in the y direction. You take what? Izz. So for this case, for bending, when your moment is in your z direction, the second moment of area is about the z direction also. Okay. So let me write this down. So stress X or sigma X is normal stresses. In the X direction.
Is MZ and IZZ still constant?
MZ is, IZZ is also constant. But
Okay.
you don't need that rule over here. Okay. That one you don't need that rule. But you're right, it's still constant. Okay.
I was thinking we were going to use calculus for some reason.
Okay. So IZZ is So normal stress is Z. So it can be Pascal or it can be PSI. And then IZZ is your second moment of area. About the z-axis, right? So this can be in meter to the power 4 or inches to the power 4. And second moment of the area, another reference term that we can use is this, also known to resistance to bending. The higher the IZZ, the higher resistance you have to bending. Okay. And then MZ is the applied moment in the Z direction. About the Z direction. So this the unit is in Newton meter or pound inch. Okay, so I'm writing both for you. And then your Y over here is the Y distance okay, measured from the neutral axis. So this can be meter or this can be inches. Now down here you see a negative sign down here. I don't want you guys to be too worried about it yet. Okay, I don't want you all to worry. Some of you might forget, hey, minus, is it minus, is it plus? I don't want you all to be too concerned about it yet. Okay. So MZ over IZZ multiplied by Y. So I don't want you all to be too worried about minus. I have a way to let you know whether is it minus or plus is true by visualization of how the structure will deform. I think that's more important than remembering vectors. Okay. Right. So when you have a applied moment like this, or you have a force like this, can anyone tell me where will the structure fail? At point A, point B, or point C? Anyone?
B.
Yeah.
B.
Yep. You're absolutely right. Okay, so the structure will fail at point B. So in any structure analysis, where do we calculate? We calculate at the location where it will fail. No point calculating some Mickey Mouse location that the structure won't fail. You're wasting your time. You're going to calculate where the structure will fail. And unfortunately, sometimes this is based on experience. Unfortunately. Okay, but let's look at the deformation of the structure. Let's look at the deformation of the structure. Okay. So let's look at the deformed pattern. And then we are going to apply the formula where we apply that stress X is equal to minus mz over izz multiplied by y. Okay. So there are a few things that are a bit confusing. Number one, why is it stress X? Number two, why is it minus? Okay, why is it that we are calculating stress X? And why is this minus over here? Okay, now So if we have a deformation pattern like this, okay, so where our structure is loaded, like how this structure is loaded, the deformation with smiling face like this. So this is the deformation pattern, right? This is our deformation pattern.
Eugene, isn't it minus because the roller will make it roll into the negative direction?
The what?
Wouldn't the roller make it roll into the negative direction when you push down on it?
No, does not work like that. Okay, let me explain to you mathematically what's going on first, okay? Right. So this is our transformation, right? X, Y, rotation about Z. And then we're going to have, so if you look at how the structure is deformed, right? At the top is going through what? Compression, right? At the top is going through compression. Why? Because the arc circumference is smaller, right? At the bottom is going for tension. So by looking at the circumference, right, you know the one where I draw compression is smaller. The circumference distance is smaller than the tension one, right? It's obvious. And because of this, how the deformation pattern look like? At this point over here, this is known as my center of curvature. Okay, at that point is where my center of curvature. So when this is deformed this way, you realize that the moment, this is the moment arrow. Okay, moment about z-axis. This is also moment about z-axis. And then because we have compression, okay, so we have compression at point alpha. So this point, I'm going to call it point alpha. And this point over here, I have point beta, right? So point alpha is compression. Point beta is at tension. So at a certain point where I'm drawing the green chain line, this point over here, this chain line is known as my centroid and also known as my neutral axis. Okay. So along the neutral axis, right? Stress in the x direction is equal to what? 0. And it has to be. Why? Because you have compression, then down here is tension. If you draw a straight line, at one point the stress is equal to 0, and that is what we call our neutral axis. Now, relative to the center of curvature, over here, when it's from the neutral axis pointing towards the center of curvature, y is positive. Okay, away from the center of curvature, y is what? Negative. So that is why when you calculate stress x at point alpha, right, our moment is still minus mz. Now y is positive. Yes or no? Divide by what? Izz. So minus times plus is still minus, so it's minus mz over izz multiplied by y, and we know point alpha is under what? Compression. Right? So if you look at stress x in the x direction at point B or at point beta, this will equal to minus mz bracket minus y now. Why minus y? The y direction is from the what? From the neutral axis, and it's pointing away from the what? Center of curvature. So this is over IZZ. So this will be equal to MZ